Hey guys, welcome to this video. So today gonna discuss about something very special kind of a model which is called as a generalized linear models. So before this video, I have already discussed about the linear regression models, the multiple linear regression models, and as well as the logistic regression models, covering about the classification type of models we can do through the linear models, right? So here, what we're gonna do is we talk about something which actually solves many of the the shortcomings we have inside a linear regression kind of a model. And if you see this GLM, so GLM is like generalized linear models. Now if you see in case of let's say linear regression model, we have certain assumptions that the target variable is belonging, or the target variable response belongs to a normal distribution, normal or a Gaussian distribution, right? Now there might be a situation in which, let's say, you want to discuss, you want to actually predict a category, or you want to predict a kind of an household income, and or like a put like a put whether an event is gonna happen or not, or let's say how many number of coffees you want to drink on a particular day. So in different kind of scenarios, the linear regression may not hold that much efficient, or even the distribution of the target variable may not be Gaussian distribution. So what is the solution is actually the generalized linear models. So generalized linear model is more like an umbrella model. So when I say umbrella models, is what I'm actually meaning is that the approach we take for the linear regression is generalized further to accommodate more I'll say more distributions, or more different type of outcomes. So what we do is that, depending upon the what kind of the distribution the target variable is actually showing, we tweak our model based on that. So let's say I have a use case in which the target variable is a normally distributed variable, right? Is a normally distributed variable. So I'm okay using the linear regression. But in another case, the target variable shows some kind of a binomial distribution. So let's say you have some values which ranges from 0 to 1. So here, this the way we I mean the way the linear regression works may not hold true. So what we do is that we use logistic regression. So what it does is that, using a logistic function, we squeeze the values of the linear regression regression values to zeros and ones, right, by using a logistic function or a sigmoid curve. Now let's take another scenario in which you are actually let's say you wanted to predict the score. Or let's say you have a score, and you want to predict the the what kind of grade up the students of a particular class is getting. So if you see that most of the classes will be, who are actually getting somewhere at values around 60 to 70, and there'll be some exceptional people who will be getting 90 or 90 plus, and there'll be some people who are really not good at some subjects and they are getting lesser values. So the distribution might look something like like this. So you have majority of your majority of the population ranging here to here. Some population, let's say this is 30, this is 40 till 70, and this is 90. So some people are there who are actually in this range, but majority of the population is in this range. So this is something that the distribution is called as a Poisson distribution. Poisson distribution. Now there are ways to solve this kind of problem by using polynomial regressor and all, but what we are actually interested in is by how we can tweak the existing the formula of having the weighted sum and solving this problem. So what you're gonna do, if you see the GLM, so GLM is actually uh, what it actually says is that, let's say if I have a distribution and I'm actually trying to get this the expected value by the help of x features. So this will be equals to a sum, weighted sum of the features x2 and so on, and this will be connected to the sum by the help of something called as a link function. So this is actually the formula of the GLM. Now if you just take a summary, we have few of the things in GLM. One which we called as link function. Second, we have the weighted sum, which in vectorized form we can give it something like this. And then finally we have this one, which is our distribution, or you can say the the target distribution, right? So you have three of the things. Now what we actually do is, depending upon what kind of distribution, there is actually a relationship between the distribution type of distribution and the link function we use. So if I take the linear regression, so if you see, linear regression formula is y, which is our expected value, that is equals to beta naught plus beta 1 x1 plus so on, right? Or I can just add an error, and this actually turns out to be of x, right? So this is the formula. Now if you just take a note of this and the formula we have here, what it actually means is that the link function here, it is actually an identity function. So identity function means that whatever the value you give to it, the same thing will get as a return. So it is identity function, and that is why in case of linear regression, which says that the y variable is a Gaussian distribution, the link function is a identity function. So Gaussian distribution, the link function is identity function, right? Let's say in case of the classification kind of, or the binary classification problem, we have used the logistic regression. And in case of logistic regression, the expected variable is basically a log odds ratio. So that is, or I can just take a natural log ln of the probability divided by the odd of it, and this whole thing again, it is equals to beta naught plus beta 1 x1 so on equals to beta transpose of x, right? So what it actually does is, if I again look up here and the link function, so the link function here is a logit, right? And the distribution is a binomial distribution, right? Let's take the third example, in which we have the award versus score problem, where we have seen the y variable, target variable, is a Poisson distribution, right? So Poisson distribution, in case of Poisson distribution, the link function is a log link function. So same thing we can actually use, we can actually use the log function to connect the weighted sum in case of Poisson distribution, and get the expected values, right? So I'll just jump on the the coding side, and we'll be doing some experiments. We'll be using both stats model and sklearn, and by that we'll also be doing like all of these three main kind of distribution. There are however many kind of distribution belonging to the exponential family. because the GLM, it actually, the distribution types belongs to the exponential family, exponential family, and every exponential family members has a link function to be connected to the weighted sum in this manner, right? Okay, let's jump on the coding side. So here we are gonna, what we're gonna do is, we're gonna just do some experiments with both sklearn and stats model. um, we'll be first taking doing some binary classification so as to simulate a binomial distribution, and then solving it through stats model, and using the GLM, in the stats model, and the same we can actually see through the logistic regression. Then we're gonna move, I have some custom data in which the response variable is belonging to a Poisson distribution, and you also gonna solve it both through sklearn as well as to the stats model, right? So I have imported some of the necessary libraries, and let me just, okay. So let's start with, I'll just do first thing, which is mm, to I'll just want to do binomial distribution simulation. Right. So if you see the in sklearn, we have something called as a make classification. So what it does is that we can actually simulate some dummy data out of it. I'm just gonna go ahead and use it. So samples, let's say I'll go ahead and make 1,000 samples, and in features, I just, for understanding purpose, I'm keeping it very simple. So 5 features, and n classes. So it, since it's a binomial distribution, so there can be only 2 classes, 0 or 1, or high or low, whatever. And yeah, so my x comma y equals to this, right? So we have got the x and y. Let us just check the shapes. But y dot shape, so we have 1,000 cross 5 and 1,000 here. So it's a vector of 1,000, length of vector is 1,000, and the matrix is 1,000 cross 5, right? So what we're gonna do is, we first gonna check, and our very own, very much familiar logistic regression, and see the coef and intercept. And then what you're gonna do is, you're gonna use this stats models GLM class to replicate the same, and check whether we are getting the same kind of response or not, right? um, so let me just quickly take this logistic regression. Okay, I'm just gonna do something like this, that um, pentest split x comma y pens. Before even doing this splitting, actually we can do something like this, that um, the x should be pd dot data frame, and what we're gonna do is that um, we create something like an x call index 1. This will be comma. So all the column, and what, sorry, all the row for each column, and then call index for call index range dot shape 1. So what this will do actually is that in this x array, we have 5 columns representing 5 different features, And since it's an numpy array, I'm just going to convert it to a data frame, and each of these 5 features will have x1, x2, x3, and till x5. So this is gonna just do some indexing in this x array and return me x. I'll just also do the head. Here we are, and we can also check the x dot shape. Doing it first here. Right. Okay, cool. So we are good to go. Now what I'm gonna do is I'm gonna do and I'll just quickly copy this whole thing. Okay. So we have data in both extrain and test. And then I'm gonna just do this simple intercept here. So the x1, x2, the x3, so on. If is these are the coefs for the features, and this is the intercept, right? Um, Now what we can do is we can just call the GLM class. So I'll just say GLM, or I can say object equals to sm dot GLM. Within that, because the stats model is more in line with the terms used by the statistician, so there are two kind of variables in sklearn. It's x and y. X are the the independent variables, and y is a dependent variable. So similarly, endogenous variable are the y variables or the target variable, and exogenous variable are the input variables or the feature variables or whatever. So ndog is my y train, and exog is the x train. Okay, so one more thing in case of the stats model, that we also need to create a column for having the intercept in the data frame itself. So we just do this at constant, right? And then we need to specify the family. So as we already know that we actually doing a binomial class. So in this case, we directly go ahead and I think it's some dot families. So binomial, and inside you can see that the link function by default it's a logit function. So you can also go ahead and define any other kind of a link function if we want to, but the default connectivity for a binomial distribution, it's a logit function, right? So sm dot families dot links dot so we have logit here. You can just do it like this, right? Got the glm object. So what I'm gonna do is we're gonna use this object to fit the model. So we have fitted, and now okay, I think we also need to store it. GLM result is to this, right? So now GLM result. Let's just take a summary. So the summary says that the coef for x1 is 0.037, x2 is -1.0, x3 is 0.66, 1.0885, and 0.2786. So if you see, the variable for this actually are quite same what we actually got in case of the logistic regression. So in a way, what I'm actually trying to infer from this, the GLM we have, depending upon what kind of distribution family we specify and the logit function, this actually generalizes to one particular logistic we already implementing. So in this case, since the data or the target variable is a binomial distribution, which in fact connects to these the weighted sum by the help of a logit function. So whenever we train and we see the coef variable, I mean coef values, this will be same to what we have seen in case of the logistic regression. So the logistic regression is actually a case or a special case of a GLM. So GLM, as I said in the theoretical discussion, that it's a umbrella term. So in this umbrella term, depending upon the family, we can actually use one particular kind of a regression, right? So we have actually shown that these are actually same. And let's just use another kind of a distribution. I'll just quickly load some data. So I have some custom data here. But if so the so this data is basically that depending upon what kind of score, maths score, it will actually give you one particular award to it, right? Now let's just implement, I mean try to plot this as a scatter plot. Scatter. Before that, I just want to rename this so that I don't want to go into that. This awards, rename it to awards and math score, right? And let's say and place it as true, right? Okay, so now what you're gonna do is I'm just gonna give the df dot math score and df dot awards and try to plot. So you can see here that if you just extrapolate this scatter plot, it actually follows a Poisson distribution here. um, Now what we're gonna do is we gonna first fit. So inside the sklearns package, we do have something called as a Poisson regressor, and we're gonna just go ahead and use it. I just copy some pieces of code from here, right? So this is my x variable and this is my y variable, right? So we have splitted it. Let's just see extrains shape. So extrain looks to be a 1D array. So what I'm gonna do is I'm just gonna convert it to a numpy array, and extrain dot values dot reshape all rows and one column. Sorry, it should be values. Cool. So we have extrain here, and let's just check the shape. I'll run this cell again. Okay. So what we have is the Poisson reg equals to Poisson regressor, and I'm gonna fit it. Let's extrain by train. So we have fit the model. Let's take the OF and Poisson reg dot intercept. So you have the the coef and the intercept. So coef of this the math score is 0.75. I'll actually explain how to interpret these values, but before that, let me also build this same model for the by using the GLM, right? So same, the drill is same, that we'll be using this the Y train and the X train, and the family here will be changing which in our case will be Poisson. And if you see in Poisson, the link, the default link belongs to the log link function. I'll just go back and change the link. So link dot, if you go here, you'll see that I do have a log link here, right? So let's just go ahead and build this. And GLM s dot, let's take summary. So you can see here the coefs here, from the sklearn as well as from the stats model, do actually match. And it's another way of inferring that you can actually tell the GLM to behave like one particular kind of a regression based on the family and the link function we provide. Now the question which actually ask for our attention is that how to interpret these values, like the the 0.761 here, right? So the way I actually try to interpret is that if the math score is getting changed by 1 marks, then the exponential of 0.07 is actually the increment, or the awards is gonna multiplied by that exponential of 0.761. So if you just take this, like this 0.761, so the the target variable will be getting multiplied by 1.08 times.